Hi guys, welcome to Know How Right Now. Today I'm going to be going over Gauss's law. We're going to try to figure out the E-field of a conducting sphere at a certain radius. So let's get started. Alright, so let's say we have a solid conducting sphere that has a charge in it. Actually, let me get my little tortilla holder, and we'll draw a solid conducting sphere. Okay, so there's our conducting sphere. We'll call it that, conducting sphere, so we don't get it confused with our Gaussian surface. Now, in order to find an E-field, well, first of all, we didn't know what the charge is, right? Let's say that we have a charge of Q is equal to 5 times 10 to the negative 8 coulombs. It really doesn't matter. But here's our charge for later on when we want to plug in. Okay, now, we want to draw a Gaussian surface. So here's a sphere. It's got a charge of Q is equal to 5 times 10 to the negative 8 coulombs. Now, just to make it easier on ourselves, let's just imagine that there's a charge somewhere in the middle here, and we have on the surface of this thing, we have an even distribution of charge, positive charge. And if you remember, a positive charge has an E-field at all points that are sort of perpendicular to its surface here. At all points it's gonna be like this. You see, it's like that. So now, in order to use Gauss's law in this particular case, we actually want to draw a Gaussian surface, and let's call this our Gaussian surface. It's a sort of a circle. So this is our, tell you what, let's write it up here. Gaussian surface. And actually I misspelled that, I think. Okay. So here's our Gaussian surface. Now we're drawing it so that actually let me write out the equation. Here's Gauss's law. The closed integral of E dot dA is equal to Q enclosed divided by epsilon naught, which is the permittivity of free space. Excuse me. So here, if we look at E dot dA, it's saying the E field with here's our dA. In this case, we have this small area which we call dA, and then we have the E field coming out of this small area, which we call E. So in this case, there's an angle right here. Well, actually, there's no angle. There's an angle of 0, and when we take E dot dA, that's really equal to E dA cosine of whatever this angle is. We'll say, okay, 0. Cosine of 0 is equal to 1. So we could just write E times dA. Now, so let's forget about the angle. There's no angle there, and that's the reason why we drew this Gaussian surface, is so that we have our E, which is parallel with respect to dA, and so now we can write this as, we're going to pull the constant out. Your E field's not changing. We're going to take the integral of dA, the closed integral of dA, and really what we're doing is we're taking the integral of this small little piece right here, and we're integrating, we're basically integrating a sphere, and so we need to know the area of a sphere. What is the area of a sphere? Well, it's area of sphere is equal to 4 pi r squared. Okay, so if we take this closed integral of dA, then really what we're left with is E times 4 pi r squared is equal to Q enclosed over epsilon naught. Okay, good. If we want to find the E field at a certain radius, then we're just going to solve for E. Supposing that we already have the radius. So E is equal to Q enclosed over epsilon naught times 4 pi r squared. Okay. Now suppose we have a we have this charge here, and suppose we have a certain area. Let's say that this area right here is 0.10 meters, and this area, this bigger area, I don't mean area, I mean radius. This is 0.10 meters, this conducting sphere, and from the center of the conducting sphere to the Gaussian surface, we have, let's say it's 0.15 meters. So that's a radius for that. This is actually the radius that we want to plug into here, okay? We don't want to plug in this one right here, this radius. But it's important to know what the radius of the sphere is, because if the Gaussian surface radius from the center of this sphere is greater than the radius of the sphere itself, then that means that there's a charge enclosed. But if there's not, let's say we drew our Gaussian surface in here. Well, the thing with that is that there's no enclosed charge. And so if there's not an enclosed charge, well then this is equal to 0. So then the E field is going to equal to 0. Because you remember 0 over pretty much anything is going to equal to 0. So now let's just say we have this radius, it's 0.15, and so we want to solve for E. Well, we've already found that Q enclosed is equal to 5 times 10 to the negative 8 coulombs, and we have the permittivity of free space, which is 8.85 times 10 to the negative 12 coulombs squared over Newton meters squared times 4 pi, and this is where we're going to insert our 0.15 meters, 0.15 meters, and we'll square that, and then we'll get an E field. So plug that into your calculator, you get an E field. Remember, if you draw your Gaussian surface, let's say your professor asks you, well, what's the E field at 0.05 meters? Well, the E field at 0.05 meters doesn't have an enclosed charge, because remember, whenever you have a charge in a surface, you actually, your charge all disperses, right? So at every point, basically if you take the entire thing in here, in this little tiny sphere, then you're not going to actually have an enclosed charge. So just remember that about Gauss's law, and you should be pretty good. Alright, well, if you have any questions, please let me know. I hope that helped you out some. Thank you for watching.